Hi, welcome to today's video about hashing. So hashing is a technique that's used to take an arbitrary message and turn it into a fixed length hash. And this is sometimes called a message digest. That's another name for a hash. And it's used outside of security as well. At the end of this lecture, we're going to look at different ways this is used, and some of them are completely outside of security, because there's a lot of times where it's very useful to have a technique to take an arbitrary size amount of data and turn into a fixed length hash and something that's repeatable. But not all hash functions can be used for security. Cryptographic hash functions are the ones we're concerned with that can be used for security. There's a lot of ways that you can convert an arbitrary amount of data into a fixed length hash, but you'd have to have certain properties if we're going to use them within cryptography. So let's look at a simple example of a hash function. Okay, so we have our data, and it's an unknown number of bits. It could be any amount. It could be very small, or it could be very large. We put that into a hash function. In this case, I just picked SHA-1. It's a real-world hash function. And SHA-1 spits out a hash that's 160 bits long. Different hash functions have different output sizes, but this is just a simple example. So we have an arbitrary amount of data that goes into the hash function, and we produce a fixed length hash of 160 bits. Now, anytime you put the same data into the same hash function, you get out the same hash. And there's no key here. So hashing by default has no key. We don't need one. The purpose of a hash function isn't to involve some sort of secret. Instead, it's just to provide a fixed way to convert an arbitrary amount of data into a fixed hash. So let's look at this sample here in Python. Actually, I'm just going to do it in the terminal right next to this. So most hash functions are implemented in a lot of different programming languages. So Python's the one that I like to use for quick prototyping. So as an example here, if I were to produce a hash function, if I were to do a hash function in Python, I would just do something like this. Hashlib.SHA-1, I'm going to use SHA-1 for my hash. And a hash function can always take an arbitrary amount of data. And usually, the language primitives for this use an update function of some sort, so you can continue to add data to the hash. So in this case, I would say, I want to hash this message. But I can add more to that. I also want this to be part of the data that is hashed. For example, I can call m.update as many times as I want, just to add more data to the overall amount that's going to be hashed. And then when I'm done, in this case, I'm just going to call m.digest. Digest is the method to produce a hash, because remember, it's also called a digest. And in this case, just because I want to print it out in something that's easily readable, because the digest is just binary data, I'm going to print it out in hex here. And so that ends up being the 160-bit hash printed in hexadecimal of the data. I want to hash this message, and I also want this to be part of the data that is hashed. All that concatenated together and hashed with SHA-1 produces this particular value. So if you repeat this program again, you get the exact same hash at the end, because when you hash the same data, you get the same result. So that's a quick sample in Python. So what are the properties of a secure hash function? I mentioned before that not every hash function is useful, only cryptographic hash functions for security purposes. So what kind of properties does a cryptographic hash function need to have? Well, first, it needs what's called pre-image resistance. And pre-image resistance means that if I'm given a hash, I'm not able to easily find the message that produced it. So we say that as it's infeasible to determine M, the message, from H of M. So if I give you a hash, you can't easily go backwards to the message. That's not easy to do. That means it's pre-image resistant. So another property of a secure hash function is called second pre-image resistance, which says that given M1, it's infeasible to find another message M2 such that the hash of M1 equals the hash of M2. So the idea here is I can't find, if you give me a message, some specific message, I can't find another message that has the same hash. So that's difficult to do. And the third property of a secure hash function is just called collision resistance. And this says that I can't find any M1, M2 such that the hash of M1 equals the hash of M2. So I can't find any two messages that have the same hash. At this point, a lot of people often stop and say, well, what's the difference between second preimage resistance and collision resistance? It seems the same. M1, M2 can't find something where they have the same hash. The difference is in second preimage resistance, I'm given a specific M1 and I need to find another message that has the same hash. In collision resistance, I just need to find any two messages that have the same hash. So collision resistance is easier to find. It's easier to break collision resistance than it is to break second preimage resistance. And we'll see a mathematical modeling of that later on in this lecture. But those are the three properties of a secure hash function. Now, if I were to say I want to break pre-image resistance, and basically that means that given a hash, I want to find a message with the same hash, what would I need to do? Okay, well, I'm probably just going to use a brute force approach. And in order to use a brute force approach, that means that I'm just going to pick some message, hash it, and compare it to the hash that I already have. And if they match, then I'm happy. Well, how long does this take? Well, that's an important question. If someone's going to brute force to try and break a hash, how long is that going to take them? Well, in the best case, so you've given me a hash, and my job's to find a message that has that hash. In the best case, I'm really lucky, and I pick some random message and I hash it, and it ends up having the same hash as the message you gave me. So I'm really happy I got it on the first guess. That's the absolute best case. In the worst case, I keep picking random messages and hashing them, and they don't match the one that you gave me, and I finally find every other hash except the one that you want me to break. I found everybody else first before I find yours. Well, in that case, if this is a 128-bit hash, that means that I found 2 to the 128 minus 1 other messages before I found one that broke the hash. That would be my worst case. That's a big number. That would take a really, really, really long time. So if the best case is 1 and the worst case is about 2 to the 128, what's the average case? How long does it take on average? Well, on average, it takes half of the worst case because you'd be halfway between the best and the worst. And half of the worst case is about 2 to the 128 over 2, which is 2 to the 127. Okay, that's still a really big number. In fact, 2 to the 127 is an absolutely enormous number. If you were to try and brute force a 128-bit hash in order to break preimage resistance, you would need to do computations for the foreseeable rest of the existence of the universe, and you would still never break it. So it's just, the number of calculations you have to do is so huge that it's not even worth anybody's time. So that would be how you could break preimage resistance with brute force, but it's just infeasible as long as the number of bits is big enough. Now, if I had a really small hash, like a 32-bit hash, well, that would be a significantly smaller number, and you might be able to break that. Okay, so how about breaking second preimage resistance? Remember, this is the case where you're given M1, and you want to find M2. That has the same hash. Well, this is basically the same as breaking preimage resistance. That's actually probably why the two names are so related, preimage resistance and second preimage resistance. It's basically the same procedure for brute force because we're effectively doing the same type of attack. So think about if you want to break second preimage resistance, it's going to be just as infeasible as normal preimage resistance in the general case. Now, what about breaking collision resistance? This idea of finding any two messages that have the same hash. In this case, things get more complicated. And in order to understand how to break collision resistance, you need to understand a part of probability theory that's called the birthday paradox. So let's create a concept that I'll call a birthday collision. And the question for a birthday collision is this. Assuming that all birthdays are equally likely, so it's equally, there's 365 days a year. Pretend for a moment that birthdays are all equally likely. How many people do I need to get into a room before 2 of them have the same birthday? So how many people do I need to get together before some 2 of them have the same birthday? If we have people in a room and 2 of them have the same birthday, let's call that a birthday collision. So how many people do I need to put together before 2 of them have the same birthday? I don't care what that birthday is. I just care about having 2 people that have the same birthday. Well, the birthday paradox is how we answer this. And the birthday paradox can be summarized in kind of a rule of thumb that says if there are n different possibilities of something, then you need about square root of n randomly chosen items in order to have a 50% chance of a collision. So in the birthday example we just did, there are 365 possible birthdays. So the square root of 365 is about 23. So the answer to our question is you need 23 random people together in a room in order to have a 50% chance of a birthday collision. That's the birthday paradox. And the reason we call it the birthday paradox is because that number seems a lot smaller than you would expect, right? You would think, well, there's 365 different birthdays. Maybe I would need 366 people in the room before I'd have a birthday collision. But just the way that the probabilities fall out, you actually only need about 23. So that's something to think about. But this is the birthday paradox. This is backed up by lots of mathematics that I'm not going to go into, and honestly, I don't understand. But what does this have to do with hashing? Well, the birthday paradox in hashing, well, remember what collision resistance says. It says that I can't find any M1, M2 such that the hash of M1 equals the hash of M2. That's similar to the idea of a birthday paradox, which would be I can't find any two people that have the same birthday. So how many hashes do I need to generate? If I were to just start randomly creating messages and hashing them, how many hashes do I need to collect before a hash collision occurs, before two messages have the same hash? Well, the birthday paradox can answer that. For a 128-bit hash, there are 2 to the 128 possible different hashes, right? So if I apply the birthday paradox, that means that I would need the square root of 2 to 128 different messages before I'd have a 50% chance of a hash collision. Well, that's about 2 to the 64, because when you do the square root of a 2 to the something, it just cuts the upper number in half. So I end up with 2 to the 64. That's still a really big number. But that means that the strength of a hash function against a collision resistance attack is only half of its strength against a pre-image attack. So if I have a 128-bit hash function, it would take me, about 2 to the 127 guesses before I could break pre-image resistance. But it would only take me 2 to the 64 before I could break collision resistance. So in a sense, we've lost half of the strength of our hash when we do it this way. So that's just something to think about. The birthday paradox is an important concept to understand when we're talking about cryptography and security in general. I'm always surprised how often it comes up. A lot of people just don't think about it, about how often something like this would happen. And I think it'll come up later in the semester too. When we talk about wireless networking and things like that. You'll be surprised. Okay, so what are some examples of some real hash functions that are in use today? MD5 is kind of the classic hash function. It was widely used for a number of years. It produces a 128-bit hash, but smart cryptographers have analyzed it, and they found that they can break collision resistance in about 2 to the 21 hashes. 2 to the 21 is not that big of a number when compared to something like 2 to the 128. So because of that, we really don't use MD5 for security reasons anymore, but it's still used widely for other things. And we'll look at some examples where it could be used later on. But because of that break in MD5, other hash functions were developed. For example, SHA-1. SHA-1 is a 160-bit hash, and SHA-1 also has some weaknesses, and collisions in it can be found in 2 to the 61 hashes. Well, that's a very, very large number. So SHA-1 is still probably okay for security reasons, and it's still used for a lot of security stuff and in software. But people are beginning to move away from it, just on the idea that, well, if it's 2 to the 61 today, maybe in a few years, people will find better attacks and it'll get lower and lower and lower. So we're currently in the security community transitioning away from SHA-1, and there's multiple options. SHA-2 is another option that people are shifting away from SHA-1 and using SHA-2, but SHA-2 is actually 4 different hash functions. Just with different names. SHA-224, 256, 384, and 512. As you can probably guess from the names, the number in the name is actually the number of bits that the hash is for that output. SHA-2 has some very, very minor attacks, but really nothing substantial, so we still consider it good and strong for security. Because remember, cryptography primitives are considered secure only if really smart people can't break them. So really smart people haven't found anything yet, but they may in the future. And another real-world hash function is called SHA-3. SHA-3 is new. In fact, it was just chosen in the last 12 months as a new standard for hashing. And there's no known attacks against SHA-3, in part because it's so new, and in part because the way it was chosen with a competitive contest means that people have already spent a lot of time looking at it, and any attacks they did find were fixed. So that's 4 sample hash functions that you'll see today. Most commonly, if you're just out looking at stuff on the internet, you'll see MD5 and SHA-1 as commonly used hash functions. So what are some applications of hash functions? What can we do with these? I'm going to talk about 4 here. There's other applications, some of which we're actually going to discuss in the class in future topics. But for now, I just thought I'd talk about 4 that we may not spend too much time on later. The first is a lot of times hash functions are used to detect errors in file transfers. Because the idea, well, I'll talk more about it, but BitTorrent, for example, does this. So BitTorrent uses hash functions to help detect errors in file transfer. Another thing hash functions are used for is message authentication codes. And this is a way of me incorporating a key into a hash function so that I can hash something and send the hash to you, but you have to know the key in order to verify the hash is correct. We'll look at that. Password storage. Hash functions are frequently used to store passwords instead of storing them in plain text. We'll look at that as well. And there are other types of usages of hash functions. This is just 3 samples. I see hashing used all over in a variety of areas of computer science. So it's a commonly used technique. And if you understand it, it'll do you well even outside of security. So the first application of hash functions is file transfer. And the idea here is that I have a distributor. Let's consider this an internet thing. So you're downloading a really big file over the internet. So you have the distributor, the person you're downloading from, and the downloader. So how do you verify that the downloader received the file correctly? Because bit errors do occur. In downloads and stuff online, you can have corruption when you download a file. So how do you fix that problem? Well, some people have said, well, you could download the file twice and then compare to make sure that both are the same. It seems like a waste, especially if it's a really huge file. So hashing is a way to solve this problem. So the distributor can host the file that they want to transmit, and they can store the hash of that file. You just feed the file into a hashing algorithm. You only have to do this once, and you produce the hash. So the distributor has the file and its hash just sitting there, waiting for people to download. So the downloader downloads the file, and they download the hash, and then they compare. They say, okay, I downloaded my file, I compute the hash of it, and I get this value. I compare that to the value that I downloaded, and if they're the same, then I'm a happy downloader. That means I have the exact same file because the hashes match, and the hash is derived from the data. If I had a bit error, if even 1 bit is different between the file that the distributor hashed and the file that I hash, then the hash value will be different. In fact, it'll be very, very different if only 1 bit is different. So hashes are really good for that. If there's an error, so if, for example, I did a download, but something went wrong, when I compute the hash, I'll get a different value than the one that I downloaded from the distributor. So that's one useful thing for using hashes for file transmission. Like I mentioned before, BitTorrent does this for blocks of data. So if you download something over BitTorrent, BitTorrent splits the data into chunks, and it computes hashes of each chunk. So after you download a hash, the client will verify or after you download a chunk, the client will also download a hash and verify that the chunk was downloaded correctly. So hashing is commonly used for something like this. Now, one potential weakness of this approach is that this is only good against errors. It's not good if someone maliciously tampers with the file. So let's say that I want to make sure that I have the original file that the author produced, so they put the file in the hash. Well, if an attacker were to break onto the distributor's computer and maybe put a virus inside of this file, well, the attacker could also produce the hash, right? Because there's nothing secret about the hashing algorithm. It's not a secret. So this type of approach only covers just general errors that aren't intentional. If it was an intentional error, an attacker trying to cause problems, then they would simply change the file and change the hash, and all the checks would pass. So what if we wanted to do that? What if we wanted to have a way to store a hash that also incorporated a secret key so that if an attacker breaks in, they can't produce a hash? Well, that's called a message authentication code. This is hashing with a key. And in this case, the goal is to create a hash that can only be created or verified by someone who knows the secret key. So you and someone else share a key, and then you can produce a hash that incorporates that key. It's not very complicated. There's a lot of different techniques, so let's look at some of the simple ones. The obvious one is I could say, well, I'm just going to hash my message, whatever it is, maybe that file, and then at the very end, before I compute the digest, I'll run one more update function to add in the key. You're effectively just appending the key onto the end of all the data, and you do the hash. The assumption there is that an attacker who doesn't know the key can't add that data, and so they can't do the hash. That approach works, but it's bad just because of how some hash functions are designed. If you put the key on the end, just the way that hash functions are done, you can make the work of the attacker a little bit easier. Still really difficult, but a little bit easier. So some people say, well, if it's bad to put the key on the end, maybe I should put it on the beginning, right? Then whatever reason that the key on the end is bad, it would be okay if it's on the beginning, and that would work as well. That's better than putting it on the end. Some people say, well, I could put it on the beginning and the end. Hey, why not just throw it everywhere? That could fix a lot of problems. And that's better still, actually. There's one way, though, and that's what this is here, where you hash twice and include the key in multiple locations. So if you use this technique for hashing, then this is called an HMAC. And this is provably good. So we'll call this an HMAC. It's just a term that we use for this particular approach. And it's provably good, meaning that someone has done a mathematical proof that says that this is a secure form of message authentication as long as the hash function is good. These others, we simply say, well, we don't know of a good way to break these two. This one, they know a good way to break this. These two, we don't know a good way to break it, but it might be possible. This last one, we can prove it's impossible to break if the hash function is good. So for that reason, a lot of people prefer to use the HMAC because whenever you have a mathematical proof, that's what we like to have. So another application of hash functions is password storage. So when you're designing an application that stores passwords, don't store them in plain text. In fact, we're going to do a whole week on passwords later in the semester where you can get more information about this. But in general, you don't store them in plain text. And the reason is pretty simple. If someone breaks into your system and steals your password file or steals your database or whatever, then they have all the user passwords. Users are dumb. They reuse passwords on different sites. They do all sorts of things that they shouldn't. You don't want someone to be able to break in, steal one file, and have all the passwords of all your users. So commonly what you do is instead of storing the password, you store the hash of a password. That way, if someone breaks in and steals the password file, they don't get passwords, they get hashed passwords. And how easy is it for an attacker to go from a hash to the password? Well, it's hard because they have to break pre-image resistance in order to do that because they have a hash and they have to find a message that hashes to that same value. So that's difficult to do. As an example, every time you hear about someone breaking, you hear about these data leaks from major corporations, right? LinkedIn had one, Adobe had one, lots of companies have had them. Adobe's happened, but Adobe said, hey, our passwords were hashed and encrypted, so it's no problem. And so just for fun, I went and downloaded a copy of the database that was hacked because it was released publicly. And you see things like this. So here, for example, is someone's account. This is their email address for their account. And this is a secure hash of their password. I can't log in as them. This is not their password. It doesn't work that way. But it is a hash of their password. So if I wanted to know what their password is, I'd have to figure out how to reverse the hash. And that's difficult. It takes a lot of processing power, and it's not as likely to happen. Now, I want to note that there are specific ways you have to do the hashing in order to make this secure. But we'll talk about those when we cover password storage more deeply later on in the semester. So summing up, hash functions take an arbitrary message and they compute a fixed length hash. They have a lot of applications in computer science outside of security. So even if you think, I'm not really going to do much with security, you should still know hash functions because they're so widely used. And we'll talk about more applications of them as the semester goes on, and we'll do a lot more in detail about the password usage of hashing later on this semester too. So thanks, and I'll see you soon.